Well, thank you all very much, and I especially want to thank Gali and all the folks from Elsevier who put this together. I mean, I am totally in awe of the presentations that have come before me, and from all of you, and even I knew almost nothing about my colleague Dan Katz, and he got his excellent presentation as well, and so we'll see. I fear that mine will not match up. But I wanted to talk to you today a little bit about the Open Science Grid. And as you can see at the bottom, it has both a DOE stamp and an NSF stamp. It's one of the rare projects that's actually funded by both agencies. So very quickly, I'm going to talk about some of the policy challenges that I run into in working with some of our project managers from the DOE and NSF. I'll talk to you about the Open Science Grid, and because this is a data conference, I will at least do one big data example, but I have to say that much more of it's going to be really about software and policy related to software, and how we can maybe make a laboratory like for doing things with software that is not unrelated to a lot of the work that I've seen now about things that you're doing with publications and those types of data sets. And software is another area that could use some work in this area. So 3 policy challenges that I've selected. There are others, but there's more that we can talk about. One is, what about sustainability when funding agencies very often have to pull the plug on funding at some point. And how do they do that? How do they make that decision? So community support. How can they, I've heard several times yesterday the whole phrase, and I use it myself a lot, how do we stop reinventing the wheel? And how can we maximize the funding opportunity by helping our community take advantage of best practices? And finally, how do I, as a funding agency, how do I actually understand what the community that I'm serving, what they really need? And you'll see at the bottom here, and this was already brought up to me today, even independent, people who make hammers, the rest of the world looks like nails. And this is very true for software developers. People who are designing and making a software product, then they're trying to find the whole world so they can fit into that software product. And so it's a very important question. So just moving to the Open Science Grid is very much a grassroots effort. And it was started by folks who happened to be in the high energy physics community who recognized that we have to collaborate. We have to have mechanisms to share our data and our processing power and our capabilities, or we're going to fail. And so it was very strongly driven, but it really began to make this work. And so it's hard to describe exactly what the Open Science Grid is. I'll jump to the bottom of my slide here. That it's a magical combination, if you will, of software and process and sociology. And it's probably about 1/3 of each. And if you take any of those pieces out, then it just doesn't fly. But the focus of the Open Science Grid, besides being a collaborative grid or a cloud infrastructure, I recognize there are some subtle differences, but the name was chosen a long time ago, Open Science Grid, and we decided not to rename it Open Science Cloud, but there's a lot of cloud technology in here as well. And it's very much focused on one particular aspect of computing, which is really high throughput computing, which is the types of programs that you can, where a user has thousands of parallel jobs or small way parallel jobs that they want to run, and they can distribute on a large network. So just to throw out some numbers to say that we really do know something about data and other things. The Open Science Grid delivers about greater than 1 million, it's 1.6 or 1.8, and every day it changes and goes up. It's trending up in the long term. Of 1 million, CPU hours every day that we deliver to our researchers. And we transfer a petabyte of data every day among the research communities that we use. We have a number, I talk about the community, the Open Science Grid community, but it's really a bunch of sub-communities. And there's, if you add them all up, there's maybe 60 or so. But in reality, there's about 20 that we consider really active, and we have a particular name for those. We call them virtual organizations, or VOs, virtual organizations. And these play a fundamental role in how we think about the Open Science Grid and how we serve our community. And the Open Science Grid, of course, has a footprint, as I mentioned, on over 100 campuses in the U.S. and abroad. Here's a picture of it. You can see the distribution. These are the number of sites, most of which contribute resources to the community. Not all of them. There are some who just use the capabilities that we provide. But you can see in the last 24 hours, and I put this snapshot probably about, I don't know, 12 hours ago, or not, it was a while ago. So, but you get the idea. Here's almost a petabyte of data that's been transferred. Here's the number of CPU hours that were used in that time period, how many jobs were submitted, and we use this and we track this data and pay attention at least to what's going on. What's being done with all that data, of course, is another question. Here's another slide. I mentioned the communities that we have, and here you can see the number of cycles used by the community. So on the top two, the red and the yellow bars, these are the two high-energy physics groups, two physics experiments, one called CMS and one called ATLAS, that are searching for the God particle, if you will, the Higgs boson at CERN. And they consume slightly more than about half the resources on the Open Science Grid. But that's really great because they contribute a much larger percentage of that to the overall grid that many of these other communities take advantage of. And you can see some of them are named here. Lots of different. LIGO was one that came up yesterday. There are a lot of different sciences represented. There's other types of physics. There are other experiments. There are, SB Grid is on here somewhere, which is bioinformatics. Mathematics. A lot of these are multi-group, so we're really doing lots of different types of sciences. So I want to try and put one of the difficulties is describing what is the Open Science Grid. And so one comparison that I make lightly is it's not unlike actually an eBay, if you will, for computational work. And the fundamental principle behind the community, if you will, Open Science Grid as a community center is really matchmaking. That we make a match between our users, our communities, our VOs who need resources and the resources on the other side. So we make that match. And as part of that match, you have a lot of other things that you need to do in order to really make this effective, to really support the community. We see the P got in the wrong place, but software, we do a tremendous amount of work with software packaging, a lot of integration and testing, monitoring, coordination. Who do people call when something goes wrong? Well, right now that would be me, but I try to not get calls, especially at night. I don't like that. So we work really hard to make this a very reliable system that the researchers can count on year after year. So if they start using it, that in the next year it's going to be there and it's going to be working. Lots of user support and the best practices. What's the best way of using this? What's the best way of getting the most out of your science on this type of a model? And so you have here the demand and the supply on one side, and all the capabilities that the Open Science Grid brings to the table, a whole fabric of services we sometimes refer to it as. Now, as people join and become to be part of this organization, which is which is very easy, it's not really much overhead, But what we find, once we have the infrastructure set up, is that the sharing tends to start happening automatically. We have a number of people share their insights on blogs. We have a number of shared mailing lists that go across the different science domains. And so people from the different science domains can start learning in many ways about what's going on, and it changes the way they do business, very dramatically. You can see this changes, in talking to them, where I sit kind of in the center. I can see these changes very, very dynamically. So just a couple other points about the Open Science Grid is that I'm not here to give you a dog and pony show. This is what we did in the United States, right? But I want to mention that the technology we've developed is designed, unlike eBay, to be replicated or to be taken to other places. And if for folks who like this infrastructure are interested in this, it's a capability that you can add on, that augments your existing infrastructure. Because as I mentioned here, as an Open Science Grid, we're the grid, but we don't own any of the resources. They're completely owned and operated independently of us. And it's the same, and just in the same model, just like eBay does not own the goods that it sells. When you buy something on eBay, eBay didn't own it. Somebody else owns it, right? But they sold it through eBay. We're providing the match, and it's exactly what we're doing here. We're also not a software development community. And this is important because, as I mentioned before, people who develop software, then all they want to do is find ways to get their software implemented. And so we're not developing science applications or even so much software tools. Now we do a tremendous amount of integration because we have to put a lot of things together. But we're not tool developers. And so we don't have necessarily that bias that says, oh, well, my tool will answer all your problems. And I've been on both sides. I've made that case before. Just one other thing is that the infrastructure can benefit communities really at all scales. And so, as I'll show you on the next slide, we have the infrastructure starts by just saying, how can I get my campus, some of the different resources on my campus, how can a researcher begin to harness those, just as a very first step. So it's not, it's very much a building block oriented so that it can be utilized in lots of different ways. And many people are starting to use pieces of our infrastructure that are not part of the Open Science Grid, and that's great and it's wonderful. And by the way, one of our classic examples for moving the infrastructure is Brazil. Brazil actually borrowed a lot of our pieces. We spent a lot of time working with them, transferring this technology so that they were able to get a grid set up across Brazil that's in use today. So here's just one example of how we're able to harness technology on site, and that is there's a little piece of integrated technology that sits near a user that is designed for a researcher to be able to install, where the researcher doesn't have to call up his IT department and say, hey, can you set this all up for me? Something that a researcher can actually put on their desktop. Now there's a caveat there. It has to be a Linux desktop, but so it's not going to serve everybody. But behind the scenes, there's often a Linux desktop that people can use. And by putting this software on, we can, and setting it up, it'll automatically talk to whatever local computational clusters there are around, and begin to users can learn to distribute their jobs across other machines on their campus, so they can start taking advantage of other things on their campus. And the beauty of this is that once the researcher starts to understand this model of sharing the resources, then it's an amazing thing happens, because they don't have to change their model then to go out onto the whole national cyber infrastructure of an Open Science Grid. They can use their same model and step out on the OSG. And one of the areas we're really working with is to be able to extend that onto the Exceed infrastructure as well. We're working, collaborating closely with Exceed to try and make this work. So that's really a description, if you will, of the Open Science Grid. I want to make just a couple of software observations, and the more I hear people talking about collecting the metrics for data, I'm recognizing here that this is really the same problem for software. And just like, publications don't stand alone, the value of the publication is when it's read and cited again, and there's a long trail. And the same is true for software. People who create software tools, a tool is not a solution. Tool, gives you typically one step or two steps, or maybe it's some combination. But it's only when these tools are integrated into an environment, a larger environment. And you see this on your, on your laptop PC. You could take any one of those tools on your PC, but it's only when you put it together into the operating system and the world you say, this is a solution. Now I can really do something with this. And the same is true with software in the wild, if you will, and especially in distributed environments where we're talking about. You need actually, one piece of software doesn't do it. You need lots of different types of components. And you need just, software, you need a security infrastructure, you need a monitoring infrastructure, you need an accounting infrastructure, you need, besides all the regular capabilities. There's another rule in the software industry is that software doesn't remain static. Software rots. And as I mentioned, there's even a Wikipedia page you can look to understand software rot. Now, what does that mean? It doesn't physically mean that the piece of software, if I put it on a floppy drive and just let it sit there, that those bits aren't necessarily changing, unless somebody comes along with a magnet, of course. But that's not really what we're talking about with rot. What I am saying is that 10 years later, you pick up that disk, and let's assume, I'll give you the benefit of the doubt that disk will still fit in a computer that you own, and you can actually still read the data. The chances are not very good that you're going to be able to get that code to run again, because the environments all around it have changed. It's the operating environments are now so different and so than they were, some number of years ago. So as the environment changes, the software becomes less valuable. So software is really only valuable for a long period of time. It has to be updated. It has to be maintained. It can't sit there. And here's an example from the Open Science Grid, the Virtual Data Toolkit, when we were first ramping this up in the early days, starting since of 02 and on further. We started to take this software and turn it into solution packages that the researchers could actually incorporate, and build on. And the number of tools and components in this package started to grow, and it's upward of 60. I think it's not growing quite at such an exponential rate since now in 2009, but it is up there, significantly higher. It's like 80 or 100. We just recently did a conversion, and I know that it's around 100 components, and that's what it takes for our community, and that's just a middleware. Even it's not. This doesn't even count the actual end applications that the researchers or scientists want to actually run. So one of the things that we do in the Open Science Grid, the VDT we call it, Virtual Data Toolkit, is that we can put together a repository where we not just put the software there, but we test all these components together. And we make sure that they're all going to work together, and what's happening is constantly, people are updating their component, sending them to us. We say, all right, we got it, we'll put it in here, and we're constantly doing this testing. It's done actually on a daily basis, so all the new software is pulled down and guaranteeing that this will at least work for the researchers and scientists. There's a lot of work that goes in here, but there's also something we discovered. We didn't make this up at the beginning, Well, what do you do when now we've got these tools, some of these components integrated into this complicated stack, and now the funding agency pulls the plug and this is no longer being supported? Ooh, what do we do? Well, what we've found is that we found or made and discovered and made this work is that we now have the ability to adopt software packages. And it doesn't mean that it's going to get all the new bells and whistles that it would if it had a steady funding stream. But what it does mean is that it's not going to rot. In other words, we're going to make sure that it maintains itself in the environment. So as things go on, I mean, one of the classics is, well, now we have to introduce a new version of Java, Java 5, Java 6, whatever. Oh, well, now we have to make some changes. So there's some minor, well, not always minor. There are changes that we have to make to the software to maintain it. But it's something that we can do as part of our service to the community. And so this begins to, at least has something to contribute to this notion and some of the difficulties of sustainability, because it gives the policymakers an option. And they can say, if I pull the plug on this, can you at least keep it going? And we can, give an answer, yes or no, or, is this a critical piece of software or not? So it becomes, this is where the work that we're doing starts to begin to interact much more with the policymakers and things that are going on. Now, as I promised, here's an example of big data. And what we're focused on here is not so much how how do you curate and package the data. What we're focused on as the Open Science Grid is, well, how do our users use the data? And when we're talking about data at scale, large numbers of petabytes of data, at least this model that's working quite well is a multi-tiered model where you have a central tier 0, if you will, that collects the data. This is at CERN, which then distributes the data to a number of tier 1 centers that are strategically located at various places all around the world. And then from the tier 1s, we have a whole network then of tier 2 centers that get the data, process the data, and the scientists work very often around the tier 2s, and then even recently we've introduced a whole layer of tier 3s, of several hundred tier 3s globally that can access this data. So the data, as it moves around, when people need to work on large amounts of data, they don't need the whole data set typically in one place, but they need the pieces, and they need the particular pieces that they want, that the researchers care about. So this is at least one model that makes it work. And as I mentioned before, it's not just one software program that makes this work. In fact, what you have to have is a whole set of software pieces here in order to make this work. And 3 different grid FTP implementations, if you know what that is. If you don't worry about it. And one piece of software here, the Berkeley Storage Manager, updated Bestman. This was one that last year the plug was pulled on it, and we adopted it because it was such a critical part of the technology to our users. So it's a model that's working, and we have actually a number of cases, examples like that. And so as we start to think about this, when we have this infrastructure built up, or when policymakers are thinking about what type of an infrastructure do you need, then all distributed software projects require code repositories, they require testing infrastructure, they require packaging capabilities, not to mention sometimes many of the other pieces that we've found we had to incorporate in order to make a solution. So why should they have to do that all by themselves? And there may be ways that we can help. So we are working, one community we've been doing a lot of work with is LIGO, where we're taking their software and we package it for them so that they don't have to. But we can use, since we have the infrastructure, it's a way for them to maximize that. So the other thing that was coming back to the title of my talk is now the Open Science Grid, we can start to think of it as a little bit of a laboratory for policymakers. And when I say laboratory, at least it's the ability for the policymakers to ask questions. They can say, what software tools does which community depend on? Which VO? Who depends on these software tools? And because if a software tool is standing out there alone, there's a good probability that it's not one that needs to be in the community. What the community needs, we pull in. We are very community driven and focused, and we do what our community wants. And because we're not biased to a particular piece of software, we will do whatever our community wants. Now, some of these software packages that come to us are, quite frankly, junk. And it takes a lot of work to get them integrated and to get them functioning in a production environment. But we've become pretty good at that over the years. And as a result, we actually put that feedback back into the development communities, and we're actually helping the software developers develop better software products as a result of this. Other questions that the policymakers can start to ask and say, well, okay, what else is needed? The open science grid is sitting right in the middle of all this work that's going on. What else do we need? What other new projects do we need? What do we not need? What's the impact if we fund this project versus this project? And so there's a real opportunity. I'm not saying that this happens, in a very large scale yet, but there's a real opportunity for policymakers to get some additional information that they wouldn't necessarily get. Now, and again, this is only one laboratory, and I'm not arguing that only this laboratory is all they need. You need a number of laboratories. But even having one laboratory, I think is a great advantage at this stage of the game. So this is my last slide. So what are the takeaways here? Is that, first off, if you have to describe the OSG, it's a combination, as I mentioned, software, process, and sociology. And there really is something that you can take home here. Any of the pieces I've talked about, are pieces that people anywhere can take, they can use, you can copy them, you can modify them, will help you. If you're interested in designing an infrastructure, a collaborative infrastructure for your scientists. And it's not, and it's actually, I didn't write this, but it's not very disruptive to the existing centers that you may have. It's something that you can incorporate right into it, because it doesn't require that you bring in tons of new hardware and various components. And finally, it's very important, the fact that we are not software developers as part of the open science grid, because then we can actually give an unbiased perspective into what's needed and what's not. We don't have anything at stake other than the benefit of our communities, and that's an important and powerful place to be. So I think I'll stop there.